Section 4.4 is on the trig functions of any angle. So we talked about the unit circle having a radius of 1 and the sine of the t for a unit circle was equal to y and the cosine was equal to x. And I told you that that's not the rest of the story. Okay? So today we're going to finish off that rest of the story. So don't memorize that y and that x too carefully, okay, until today. We're going to let theta be an angle in standard position with xy a point on the terminal side of theta and r being equal to the square root of x squared plus y squared, and r can't be 0. Okay, formal definition. Okay? In other words, if I drop, thought I oriented, I'm sorry. In other words, if I drop a perpendicular from the terminal ray to the x-axis, wherever it happens to be. Okay? This is my height of a right triangle that's formed. That's my y. This is my x. This is my r. How did they get r equals the square root of x squared plus y squared? Because of Pythagorean theorem. X squared plus y squared equals r squared, so r will be the square root of the sum of those squares. Okay? So the sine of y, sine of theta is not just y, it should be y over r. Okay? Because the sine of theta is going to be the opposite over the hypotenuse if we take it back to the triangle form. The cosine is going to be the adjacent over the hypotenuse, x over r. And the tangent's the opposite over the adjacent, y over x. And the reciprocals still hold. Cosine will be, the cosecant will be r over y. The secant will be r over x. Cotangent will be y over x. I don't know why the textbook mixed them up, but I took a screenshot from the textbook. Okay? Rachel, let's put it away, please. Okay? So, if 7, 4 is a point on the terminal side of theta, and they want us to find the sine, cosine, and tangent of theta, we know our x is 7, our y is -4. The sine of theta is y over r. We have to figure out what r is first. So we'll square the 7, square the -4, and take the square root of it to get our r. 49 plus 16, square root of 65. No perfect squares there. Okay? So we have our y value over the square root of 65, and we don't like to leave that with a radical in the denominator, so we're going to make that -4 square root of 65 over 65. Okay? We'll do the easy one next. The cosecant means simply flip them. So don't flip this guy. Flip this guy. Okay, we'll do cosine too, but I'm going to go with cosecant next. And just flip my sign, but flip the intermediate step before you rationalize it. Square root of 65 over -4. Okay? Now let's do the cosine. Cosine of theta, x over r. So 7 over square root of 65, which is going to be 7 square root of 65 over 65 when we rationalize the denominator. Okay? But secant, use this intermediate step and find the reciprocal. Square root of 65 over 7. Okay? Tangent. Okay? Y over x over r. R's go away, we'll get y over x. You can't if you don't remember these two. So y over x is -4 over 7. So the cotangent doesn't matter where you put your negative, -7/4. Okay, that's the ratio of those sides for that particular angle. Everybody good? Okay. Trig functions for any angle, not just on a unit circle. Absolutely, I'm sorry. Okay, here we go. Given the cosine of theta is 2/3, and the tangent is greater than 0, okay, tangent's positive, okay, we want to find the cosecant of theta. Cosecant is the reciprocal of sine. So we've got to use this to figure out what sine is. Okay? Cosine of theta, x over r, right? Okay? So we know our x value is 2. We don't know what our y value is. Okay? A squared plus b squared equals c squared. Our c is the hypotenuse. So r squared, or 3, is equal to the square root of x squared plus y squared. Okay? 4 plus y squared equals 3. So 9 will be 4 plus y squared if I want to clear my parentheses, my square root. Taking away 4, y squared is 5. So y is square root of 5. Plus or minus potentially, right? But they're saying that the tangent is greater than 0. Okay? So if the tangent's positive, can we use this negative value? No, it's got to be positive square root of 5. Okay, so that's my y. So to find the cosecant, sine is so we just need to put the r over y to find the cosecant. Our r we said was 3. Our y we said was the square root of 5. And we rationalize. Okay. All I did here was said I don't like the square root, so I'm going to square both sides. to get the 9. I did it 2 things in the same step, and I squared my 2 at the same time. Okay? And we can't leave this as a radical, so 3 square roots of 5 over 5. Everybody good? Okay. This is going to help you remember things. Okay, this is your quadrant 1. Reference angles is what it's labeled on your outside of your foldable. In quadrant 1, everybody's positive. My x is positive, my y is positive, my radius of my circle is positive, so everybody's positive there. Okay. Quadrant 2, x is negative, and y is positive, and r is always positive. So when the x is negative, that's going to make the cosine and the tangent be negative. The sine and cosecant will be positive. In the third quadrant, x and y are both negative. So that means that the sine is going to be negative, the cosine is going to be negative, but when we take a negative over a negative for the tangent, it'll be positive, as will its its reciprocal function. Its cofunction. And finally, in our quadrant 4, x is positive, y is positive. That makes the sine negative, and it makes the tangent negative, but the cosine and secant will be positive. The way I remember it is I was always taught, and this isn't true, isn't a true statement maybe for all of you, all students take calculus. Okay? That will help you remember that all are positive in the first quadrant, sine is positive in the second, tangent's positive along with its reciprocal in the third, and in the fourth is cosine and secant. I was trying to come up, I spent way too many brain cycles on this. Quadrant 1, 2, 3, 4, all something, something, core, always something to the core. I couldn't come up with something. Okay, so if you come up with a better mnemonic that doesn't say something that's not true, because not all students take calc. There you go. I like that. All students take classes either. Okay. All right, so here's how this works. We use reference angles. The reference angles help us figure out which quadrant we're in and whether the value is going to be positive or negative for the individual trig functions. If we're in quadrant 2, it's like dropping a perpendicular to the x-axis, and this will be your reference angle, theta prime. Okay? It's 180 degrees or pi minus whatever this is for the reference angle. Okay? For the second one, if our reference angle is in the third quadrant, then it's like dropping a perpendicular to the x-axis again. And if we take theta minus pi or theta minus 180, that gives us our theta prime that we're looking for. Okay, our reference angle. Exactly. Yep. However much more you would need to get to here, or however much was left when you subtracted. Okay. So perfect example. Let's say that we're talking about this looks like it's about a 135 degree angle. So if this is 135, 180 minus 135 is a 45 degree angle. And it's going to behave just like a 45, sine, cosine, tangent, and everything. It's just that we have to remember that everybody's positive here. The sine is positive there, so cosine and tangent will be negative. Okay. Fourth quadrant, we've wrapped all the way around. We just need to know how much is left to make that full complete circle. So we would take 2 pi minus the theta in radians, or 360 minus the theta in radians to figure out that last part. And that's your theta prime. Okay. Let's work on a couple problems. Find the reference angle for 144 degrees. Sketch a quick chart, a quick axis, coordinate plane. 144 is where? First, second, third, or fourth quadrant? Second quadrant, okay? So it's going to be a little more than 135, right? Something like that. So am I going to add it to 180 or subtract it from 180? Subtract from 180. 180 minus 144 is, that's your theta prime. And the 144 was your theta. Reference angle 36. Okay. 5 pi over 4. Quick sketch. Pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. Right? We're counting by pi's over 4. Okay. Those are going to be easy. It's just a pi over 4 reference angle, isn't it? It's a pi plus another pi over 4. So pi over 4. When I counted them out, I was here. So 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. Okay, so I have to take off pi. I take 5 pi over 4, and I take away a pi, which is 4 pi over 4, to get pi over 4 radians. Okay. 7 pi over 9. This one's tougher. So we have to think about where this one would end up. If you want, you could turn it into degrees. I would not be any the wiser if you're more comfortable with that. It's the strategy I would use if I were under pressure and in a hurry. Okay? But think about this. This is pi, right? Okay? So where would 7/9 of it be? Over here or over here? Over here, yep. So if I were splitting this into 9 equal parts, 7/9 of it is going to be over here somewhere. Make sense? Okay. I'm probably closer this way. I'm probably a little big, or a little small, I guess, as the reference angle goes. Okay. So if this is 7 pi over 9, this is going to be 2 pi over 9, because how much is left of that pi? 2 pi over 9. Okay. So think about them in terms of fractions, but your semicircle is your pi, or your half of the rotation around it. Okay. 1.7. Okay. 1.7 is something that's already got pi multiplied in. Okay. All the way here is 3.14 pi radians, or 3.14 radians, right? Okay. So 1.7 is going to be a little bit more than 3.14 is half of 3.14 is 1.17, right? So more than 1.17, it's going to be somewhere over here. Okay. So you would take 3.14 minus the 1.7 and get whatever is left. Okay. No mind boggling on that one. Okay. All right, last one. Trig values of common angles. It's going to be in your best interest to memorize these guys. The quicker you memorize them, the sharper you'll be. So first of all, let's do our conversions quick. Radians, 0 degrees, 0 radians. 30 degrees, pi over 6. Smallest angle has the biggest denominator. You should know our pi's over 6s, our pi's over 4s, our pi's over 3s, and our pi's over 2s. 45. Pi over 4. 4 and 45. Pi over 4 in radians. 60. Pi over 3. That's the smallest one that we're expected to know from memory. Except for 90, which is pi over 2. Half of that. Half of that first part. 180 pi. And 270. 1.5 pi, 3 pi over 2. Okay. Sine of 0. 0, we're at 1 over and 0 up. So what's the sine of 0? 0. Okay. Sine of 30. Sine of 30. 1/2. Sine of 45. Square root of 2 over 2. Sine of 60. Square root of 3 over 2. Now reverse them. Okay. Cosine. Square root of 3 over 2 for the 30, because they're cofunctions. They're 90 degrees separated. Cosine is going to be the same for 45, and 1/2 for the cosine of 60. Think of them as catty corner. Okay. Cosine of 0. 1. That's the x value of our 0. Okay. Let's do these guys. 90. At 90, we are 0 over 1 up. So what's the sine of 90? 1. Okay. Cosine of 90? 0. Okay. These guys are flipped. Okay. 180. At 180, we are 1 back, 0 up. So 0 for sine, -1 for cosine. Okay. At 270, we are 0 over and -1 down. So sine is -1, cosine is 0. Okay. Once you have that filled out, now tangents just sine over cosine if you don't want to memorize them. Sine over cosine, 0 over 1. Sine over cosine is the tangent. So 0 here. Okay. Sine over cosine, 1 over 2 over the square root of 3 over 2. This is the one with all the 3's, square root of 3 over 3. 45, square root of 2 over 2 over square root of 2 over 2. Square root of 4, or 4 over 4, right? So when we flip these guys, or this over this, it's going to be a 1. Okay? And square root of 3 over 2 over 1/2, square root of 3. Here's where it gets interesting. Is there such a thing as a tangent of 90 degrees? No, we can never divide by 0. This is undefined. Tangent of 180. Tangent of 270. Undefined, yep. We can never divide by 0. 1 over 0, 0 over 1's okay. 1 over 0 not. Okay. Tangent's always the sine over the cosine. Okay. Memorize this table, or at least the top 2 rows, and you can derive the rest of them. Okay. So we can use that to figure out what's going on here. Okay. Cosine -60. Cosine's an even function, right? So it's the same as the cosine of 60. What's the cosine of 60? 1/2. Or you can say I'm down here at a 60-degree angle in the fourth quadrant. All students take classes. That guy is a 60-degree angle, and cosine's positive, so 1/2. Sine of 5 pi over 3. 60 degrees, right? Which quadrant? Pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, right? Okay, so we are in quadrant 4. Is sine positive or negative? Negative. So we want the negative of the sine of 60. Negative square root of 3 over 2. Got to memorize that table. Okay. 17 pi over 6. Holy smokes. 12 pi over 6 is a full rotation, right? Okay, so we need 5 more pi over 6, don't we? Okay, so 5 pi over 6. Yep, 5 pi over 6 is going to be in quadrant 2, isn't it? It's going to be a 30-degree angle in quadrant 2. So 30-degree angle has all those 3's, right, for tangent. And all students take classes. T is not positive, so negative. Okay? I went through those quickly. Hopefully that makes sense. Okay? Let theta be an angle in quadrant 3 such that sine is negative 5/13. Okay? The y is a 5. 13 is the r. And we're going to be negative on the y part because our radius will never be negative. They want us to find the secant and the tangent using trig identities. So r over secant is the 1 over the cosine, so that's going to be an r over x. You could use Pythagorean theorem. They want us to use the identities. But yes, you could use the x, r equals the square root of x squared plus y squared. Okay. Secant and tangent. Okay, let's work it that way. 13 is our r, so 13 equals the square root of x squared plus negative 5 squared. So if I want to square both sides to get rid of the radical, 169 equals x squared plus 25. Subtracting 25 from both sides, I squared both sides to make that. Okay. So 144. So x is 12. Okay. So our secant is going to be 13/12. And our tangent, negative 5 over 12. Okay, we'll talk about the trig identities next chapter some more, so we don't have to use that method. Okay. I think you guys can do all of these, right? Now, there's your assignment.